Hi everyone, this is Amy St. Croix with the Statistics Division. I would like to welcome you to our webinar today and thank you for joining us on this Friday afternoon. We do realize that it takes a certain level of dedication to take time out of your day on a Friday to be with us, so we thank you for that. Our speaker today is going to be Mr. Bob Doring, who has been in the quality field for over 20 years. He is currently a quality engineer for an automotive component manufacturing firm, as well as a consultant in SPC, metrology, and quality concepts training. He holds associate's degrees from Lorain County Community College of Elyria, Ohio, and the University of Akron, Ohio. He has a bachelor's in business and an MBA in systems management from Baldwin Wallace College in Ohio. Today, Mr. Doring will be presenting on the topic of the correct use of non-Shewhart SPC in precision machining, which this is a topic that has received much attention lately. Please note that during the webinar, all of the phones and microphones other than mine and Mr. Doring's have been muted. So if you have questions or comments during the webinar, please use the questions interface in the GoToMeeting control panel. I will hold all of these questions for the end of the presentation, at which time Bob will have some time to answer those for us. So at this time, I'm going to hand things over to you, Mr. Doring. And thank you again for presenting with us today.
Thank you. I can, you see my mouse on the screen there?
Yes, I'm just going to give you control of the screen so that we can see your slides. And I'm doing that at this time. Okay, we can see your slides.
Okay, thank you very much. Well, let's get started. Great, that's going to come in handy because I'm used to pointing at screens, and we may need that. Okay, the first thing I want to do is define statistical process control. We're going to start with the basics because sometimes it becomes an issue, and we're going to need to get past this right away. So remember that statistical process control is the monitoring and reaction to a process based on statistical methodologies. So based on that, Shewhart charts in and of themselves are only a subset of all statistical process control methodologies. There are others, and one of those we're going to discuss today. SPC charting is typically found in precision machining operations. But what we tend to find is perhaps X-bar and R charts, maybe individuals moving range charts, and often we find compressed control limits. We also find capability indices that are too high or too low, or even bimodal distributions. But the real thing is, it can't be that bad. Why are we finding these conditions if it's not that bad? Well, we'll take a look at it. First of all, I like to use the automotive industry as a benchmark because they have a lot of people that have been able to take a lot of time to sort through these things. And what we have here is the AIAG PPAP 4th edition in section 2.2.11.3, acceptance criteria for initial studies. People are probably very familiar with this, especially these indices that you see at the bottom, the 133 and 167. Being acceptable or unacceptable for capability studies. But often people stop there. Yet there's more. In 2.2.11.5, there's processes with one-sided specifications or non-normal distributions. And in this case, it says the organization shall determine with authorized customer representative alternative acceptance criteria for processes with one-sided specifications or non-normal distributions. In automotive terms, that means we're not really sure what to tell you, so you're going to have to go ask your SQE. And then it says the above mentioned acceptance criteria that we saw before, the 133, the 166, assume normality and a two-sided specification with the target in the center. When this is not true, using this analysis may result in unreliable information. You might have to use alternative acceptance criteria, which would require a different type of index or some method of transformation of the data. Well, transformation of the data is handy, especially for those people I like to refer to as normal centrics. Those are the people who really only understand statistics if they're in the form of a normal distribution. But that's not normally or typically a good idea. The focus should be on understanding reasons for the non-normality, which we will do today. For example, is it stable over time? And how to manage the variation, which we'll also do today. So how do most people choose their control charts? Well, unfortunately, many people have just got a giant X bar and R chart stamp and have gone through the process of stamping them all over the plant. The X bar and R stamps aren't the best, but the reason why they tend to do it is they believe the urban legend that X bar and R charts work for any distribution. Well, they don't. Let's take a look at the normal process and go back to exactly what we expect to see in a normal process. In order for a process to be normal, it should be able to be set at the mean. It will continue to randomly vary about the mean. And here's a key point: without any operator intervention. So what kind of a process actually does that? Well, let's talk about cutting the grass, for example. There you set the mower at a certain height, and then you go out, as most quality professionals may do, with your depth gauge or caliper and measure each blade of grass. You will find that each blade of grass is independent. Most of them are going to be at a certain height based on whatever you set the mower at, some a little higher, some a little lower. Random and independent, that's going to be key, and that will give you normal variation. What's control? A process in control is in the ideal state of 100% conforming and predictable. It must remain stable over time, must operate in a stable and consistent manner, must be set at the proper level, that is somewhere in between the specifications in order to be capable. There's two types of causes, and there's a little bit of debate on exactly what falls into these categories, but since I'm doing the presentation, I get to define them. We have the common cause, which we know to be inherent in the process. It affects every part. For example, gravity, air pressure, and tool wear. That's right, tool wear is a common cause. Why? It affects every part and it's inherent in the process. You can't get rid of it. It's a common cause. Now, as far as special causes, they're assignable. They do not affect every part. For example, tool breakage, startup, change of operators, change of lot materials. Those are assignable. They come, they go. So in traditional SPC, it expects that all special causes have been eliminated, at least in the period of time that you're running in control. It expects the remaining variation to be random, with most of the variation close to the central value. It seeks to find trends from within an otherwise random output to act upon when they occur. Let's take a look at this as an example of the type of data we would expect to see. It's kind of like looking out into space looking for signs of life. What we generally see is noise, random. But if we can find a pattern shows intent, something that we don't expect to see. If we find such a trend, then we can take action to determine its origin. This is really more monitoring than control, but that's exactly what we're doing with traditional Shewhart charts. Now, one of the things I want to take a look at is a total variance equation. What it states is that total variance is a sum of all the other variances in the process. One of the key variations we're going to be looking at is tool wear and its effect on the dimension. But there's other ones in there too, such as measurement error, gauge error, material, temperature. All these things are additive. And not only that, they can have their own distributions. They may have normal distributions, they may have non-normal distributions, and all these various distributions will add up. The variances that affect an output are additive. We saw that in the total variance equation. They're asynchronous. That means that each can change at different levels at any time. They don't trend along with each other. And not only that, they're multimodal. You have various types of distributions unless one variation source vastly outweighs all others. And that can sometimes be your gauge error masking your process variation. That's why it's key to make sure that your gauges are correct with adequate resolution and discrimination, and their use is correct also. We'll get into that a little bit more in a minute. So let's define what precision machining is. It's a process where material is removed by a cutting surface, such as grinding, honing, turning, milling, etc. In order to be precision machining, the process must be controlled in a manner that all variation, vibration, bearings, gauge, is held at a statistically insignificant level except tool wear. Now what we see when we are observing tool wear, and in this case it would be an OD, is that over time the diameter will start to increase. If nothing is done, it will increase to a level that it's going to be out of specification and of no value. So in order to accommodate that, we have to make an adjustment. So what happens over the wear, adjust, we get a curve that we refer to as the sawtooth curve. If you take a look at the sawtooth curve as a frequency, you'll note that the dimensions get larger and larger and larger, and then they return to smaller when you make the adjustment, larger and larger and larger, smaller. And the distribution that you result with is a rectangular distribution, not a bell curve distribution. That means that this sawtooth curve generates a non-normal distribution. Is it stable? Well, a rectangle is pretty stable, so we're going to say that it is at this point. What we have when you have a rectangular distribution is the continuous uniform distribution. Now it's important to note that this is the continuous uniform distribution. It's quite different than the discrete uniform distribution. That's the uniform distribution you get if you take a die, for example, and roll it. Each individual value is random and independent when you roll a die. But that's not what's occurring with tool wear. It is actually a time function. So don't use the statistics of the uniform distribution. We have to use the continuous uniform distribution to use the correct statistics. Now some people say, well, you know, we don't believe anything unless we see a journal article, so okay, fine. Here's a journal article called Process Control and Evaluation in the Presence of Systemic Assignable Cause. This was printed back in 1997, and of course, they call it an assignable cause. It's incorrectly identified as much, but let's see what they came up with. In this journal article, they took 50 consecutive pieces and collected them from a bar grinding process. They were measured over a cycle and measured for the diameter. And what they discovered was, in the grinding operation, over time, the dimension gets larger. That's good data. Then they discovered that over time, if you get to a point, you're going to have to make an adjustment or else it's going to get too large. Now they came up with some pretty unusual calculations to determine when to make the adjustment that weren't exactly right. But one of the things they did identify for sure is that you have a sawtooth curve with machine variation from tool wear. And that's important. Now we'll go back to AIAG in the SPC second edition, and what they've identified is repeating patterns. And the way they described it was, there are times when repetitive patterns are present in control charts due to known assignable causes. Well, it's not really an assignable cause. It's a common cause that you can give it a name, but it's not a special cause. But we'll continue. It's a cause that cannot be economically eliminated. That's right. You can't eliminate tool wear economically. But then they continue. When these types of repetitive patterns exist, the average chart will exhibit conditions associated with an out-of-control process, since there is, in their terms, economically influenced special cause acting on the process. Well, it's true. What happens is you have a trend, and you might think that a trend is an out-of-control condition, but it's not. You expect it, so it's not out of control. The influence of this special cause can be shown to be predictable over time, and additional variation is acceptable to the customer. Now, that's a question I posed. Do you think the customer is accepted tool wear? I mean, they really don't have much of a choice if you're doing machining. The process controls then can be modified to allow it, and we're going to show you the correct process controls in order to control tool wear. Well, people will say, but the X-bar chart should be perfectly fine because Shewhart charts have been shown to be supported by the central limit theorem. Let's take a look at the central limit theorem with a little bit of detail. It states that sufficiently large number of independent random variables, each with a finite mean and variance, will be approximately normally distributed. Note, independent random variables. That's key. Precision machining has a sufficiently large number of, well, are they independent? No, they're not independent. They're a time function, so they're dependent. Are they random? No, they're not random. They are actually a function, so they are non-random variables, each with a finite mean and variance, so they will not be normally distributed. Therefore, the central limit theorem does not apply. Well, how about Chevyshev's inequality? Again, Chevyshev's inequality gives an upper and lower bound of probability that a value of random independent variable with finite variance lies within a certain distance from the variable's mean. But we're not talking about random or independent variables, so it doesn't apply. In fact, what's really interesting about this is that in machining with tool wear, the mean has no real value in controlling the process with the uniform distribution. It doesn't really care about the mean. All it cares about is the two edges of the distribution. And what's even more interesting is running to the mean, which is what the poor operators have to do if they don't have a charting methodology, is really not how to control a process with a uniform distribution. In fact, running to the mean, which means adjusting constantly to try to keep it at the mean, is over control, something that you actually want to avoid because you become the process. Now, there's a couple of charting methodologies we can look at. We see them on the shop floor, but let's see which one is actually the best. We have the X-bar and R, the individual moving range, and there's a new one I want to show you today, not really too new, but it might be new to you, called the X-hilo R. Well, which is the best? Well, let's look at the standard X-bar and R control chart. We're all fairly familiar with that. However, how do we actually generate the data for this? Well, here's a typical way that we generate it. We get a sample of 5 parts, let's say, and on each of those 5 parts, we'll take one diameter. And from those diameters, we'll do the average, and we'll also search for the range by subtracting the highest from the lowest. Now, let's think for a moment what that really means. Here's a trick question. When you're machining a round part, how many diameters are there in a circle? Well, actually, there's an infinite number of diameters in that circular feature. Yet, how many did you measure? You only measured 1. What's the statistical significance of a sample of 1 out of infinity? Well, unless you're a lottery winner, it's not very impressive at all. In fact, if you take a look at a circular feature, you're measuring 1 out of, oh, it could be any diameter, because you have this roundness issue that's not perfect. So the real problem is, what diameter did you measure? And what does the difference in the diameters that you measured across 5 parts really represent? This also is true for a length. It's not necessarily only diameters, because when you're doing a length, you might have a variety of lengths across a feature. So here's the problem, and let me go back for a second. You are measuring 1 out of an infinite number. There's got to be a better way to resolve this particular problem, and there is. So another thing that occurs is you have an X bar and R chart generally with ridiculously tight control limits for precision machining. And here's why. This calculation right here, when you're doing precision machining, what is the difference in, let's say, 5 consecutive parts? In precision machining, there's very little. So that means that the range of your sample is going to be virtually 0. That being the case, all you're going to have is the average and very little calculation for that variation. So you're going to have extremely tight control limits about your average. The variation that you are going to see, though, is measurement error. Not gauge error, measurement error. Again, that goes back to the fact that you only took 1 diameter out of an infinite number. So the only variation you're seeing is the variation based on the issue with roundness, which has nothing to do with variation over time. That's a within part error. So the X bar chart from the X bar and R charts represents the average of an insignificant sample of measurements of a circular feature. That's not very useful. Measuring multiple samples is a waste of time in precision machining, because several samples closely related in time are going to be very similar. And then the R charts represent the range of measurement error. All you're picking up is the variation from roundness, not the variation from the process over time. You're picking up essentially within part variation instead of over time. And then on top of that, the control limits are calculated using statistics for the wrong distribution. They're based on the normal distribution. You have a continuous uniform distribution. You have the same problem with a pre-control chart. Again, you're only picking up 1 diameter out of all of the diameters. So it's also statistically insignificant. Now with the moving range chart, you resolve the problem of measuring a lot of parts at one time that are going to be similar, but again, you still haven't resolved the problem of trying to measure all of the diameters within a circular feature and controlling them. So again, this still is not the best chart for this situation. Now the rule number 1 from Shewhart, and if we're going to do SPC, we're going to have to use Shewhart because we need to get some street cred. The original data should be presented in a way that will preserve the evidence of the original data for all the predictions assumed to be useful. So we want to use the actual data to generate the information. We don't want to do any transformations. We want to use it as it's generated to preserve that evidence. Also, a rule of life, perhaps you're aware of this or have been affected by it. If you measure 1 diameter, you'll measure a good one. And the customer will probably measure a bad one. So we got to get past this issue of measuring 1 diameter and measure something representative of all diameters. So how do you control all diameters? Here's the key. Instead of measuring 5 parts, let's take some quality time and measure 1. We'll measure about that part, and we're going to record the largest and the smallest diameters from that part. What does that tell us? Well, if you have the largest and the smallest, that means everything's in between. If you're controlling those two, you're controlling all possible diameters. That's far cry better than measuring one than having statistically insignificant data. So in this example, we're going to measure several locations, and we're going to use that information to generate the high and the low value. Now, of course, the more values you can get, the better. But at least now we're going to capture some of the values to try to collect information from that within variation from roundness. What else can you learn from the largest and smallest diameter? Well, the difference between the largest and the smallest radii, by definition, is the roundness. Although technically the difference between the largest and smallest radii is roundness in GD and T, we're going to choose to measure smallest and largest diameters so that our data stays in the same context. We're going to have the largest and smallest diameters and the range be in terms of diameters. It doesn't really matter because it exhibits the same signals. It's only a factor of 2. And it also keeps the charts consistent in terms of diameters. Now, if we take a look at a control chart using that characteristic, you can see that we're measuring the largest diameter and the smallest diameter, and we're watching that variation as the tool wears. We're capturing roundness in between there. So all diameters are now within control. We don't have any diameters that we're not looking at because we didn't measure them as we had previously. The area between there, that represents the roundness. What happens is when you get to the upper control limit with the maximum diameter, you adjust it so that it's down to the lower control limit with the minimum diameter and continue on. If you had only measured one diameter, you would see this kind of variation occur on the black line. However, that variation is variation from measurement error. It has nothing to do with the process variation. It's because you did not capture all of the diameters. That's not process variation, that's measurement error. And what you are concerned about is capturing process variation so you can make decisions on the process. Measurement error does not provide process information. And that's one of the problems with the trend chart. What people try to do is generate a chart about the variation that they see on this chart when it's actually trending up from the tool wear. But all they're looking at is measurement error. And it's a very difficult chart to actually generate, and it has nothing to do with process variation. So it's really a waste and a useless chart. Now let's also take a look at this. Once again, the tool wear is a key component of the total variance equation that we're trying to control. However, the trend chart ignores it and looks at everything else. Well, if it's the major variance, why would we ignore it and look at everything else? That's not really of any importance to what we're trying to do to control the process. So again, that shows that the trend chart, although some people tend to think it's a great chart for tool wear, it's difficult to prepare and maintain. It's difficult to train and use. It has an invalid statistical basis for its control. That is, it's looking at measurement error instead of process error, and it provides little useful information for the control of the process. Let's take a look at the X high-low R chart. Now here you can see the X high-low R chart. The range is the roundness, and that provides some valuable information. In fact, this is what it looks like when it's prepared on the shop floor. You can see the roundness in the process. Once you have the upper control up the largest diameter of the sample out of control, you work to adjust it so that the lower is in the lower control limit, and then allow the process to continue on. Now, just like you would expect in real SPC charting, when you make an adjustment, you should mark what that adjustment is. That way you know that this process didn't do this on its own, because it could, and that's not a good thing. You want to know when there's a shift that it was an intentional shift. And in this case, you can see that because they told you on the chart that they made that adjustment, and that's good. Now, one of the issues that people have is, what is the sampling frequency? For X-bar and R charts, generally you have two techniques used for sampling frequency determination. One is the dartboard approach. You saw it as let's do it, I don't know, every 15 minutes. The second one is the operator whining approach. And that's where they say, well, you know, that's too many times. We don't have time to do that. So, okay, we'll do it every hour or every 2 hours. Okay. Neither one of those are very meaningful. However, in the X-high-low R charting sampling, it's actually a sane sampling frequency. What we're looking at is the time it takes for the process to go from the lower control limit to the upper control limit. And we take that sampling time and divide it by 5. If it takes a week to make that change, well, then you could do one every day if it wasn't for needing to take more data just to make sure you're not missing any special causes. But if it makes this transition within an hour, that means you have to do it several times an hour, or the process is going to go beyond your control limits, and you're not going to have any idea what to do. So a recommendation is 5 data points between adjustments. Once again, the continuous control, the continuous uniform distribution is what we're doing. And what does it really care about? These 2 points right here, A and B, what are they? Those are the 2 points that you're adjusting between. So those are the 2 key issues, and you need to determine, well, how do you decide where to put those 2 points? Now, in a perfect world, you could make those 2 points the specification, but it's not a perfect world. So we know we have to accommodate all these other errors that can show up. So essentially, we need to have some bounce area out there for that. So what we do is we take a look at the area between the specifications and say, well, Shewhart allows you 99.73%, but then they have very low distribution out here. For what we're doing, the best is a 75%. That's a rule of thumb for these control limits. 75%. Now, what can that mean to us? It's a guard banding to protect from the remaining sources of variances. And if you take a look at the capability is the specification, the distance in the specification, or the upper specification divided by the lower specification, divided by the upper control limit minus the lower control limit. Well, if the control limits are based on specification, which they are in this distribution, 75% of that gives you a 133 capability. It's not the kind of capability, it's not CPK, because that's all based on normal distribution. But it gives you a ballpark of what you're looking at. Now, what's the effect of increasing the capability? That is reducing the variation and increasing the capability to 166 or even 2. Well, what happens is you compress the control limits, and that causes you to do more adjustments. Well, is more adjustments a good thing? Not necessarily, because that means you have more operator intervention. And the more the operator has to intervene, really the more participation they have in variation. So you really don't want to decrease the control limits unless it's absolutely necessary. So how do you evaluate an X-high-low R chart? Well, first of all, you expect a trend. Tool wear is a trend. But what you're looking for is a trend in the wrong direction. So, for example, if you're doing an OD, you expect the trends to to be larger and larger diameters. If for some reason suddenly it starts getting smaller and smaller, hey, you don't expect that. You need to investigate what's causing that. Now, on some occasion, you can see that, especially with roughing finishing operations. And the reason for that is the roughing tool wears at a different rate than a finishing tool. And that causes a change in tool pressure that can affect the finish dimension. So essentially what happens is you don't get that perfect sawtooth that you would get, for example, with grinding. But as long as you know what the cause is, you can continue on. Generally what you see is a kind of a hook type of thing because of that. But if you see it going totally against what you expect, you need to stop and assess the problem. You might have bearings that are failing. You might have tools coming loose. You might have tool breakage. You need to take a look. If the range starts to increase, that means the roundness is getting worse, or parallelism if you're looking at a length. That is a key factor that you need to take a look at because it's actually a leading indicator of tool wear. That's right. Range changing is a leading indicator of tool wear. In fact, it gives you a clue that allows you to change the tools maybe before it even breaks. You won't get that kind of information from an X-bar and R chart. So what happens is, let me go back. What happens is you have a continuum. You have a continuum from cutting to rubbing as a tool wears. It starts off cutting, then it starts to rub. The more rubs, the more it transfers the variation of the machine to the dimension, and you get more and more roundness. Also, the more it rubs, the more it starts to generate heat, and it's going to create heat to either harden and crack or just simply essentially explode the cutting edge of that part. So when you see this happening, you can actually tell by experience when there's enough roundness occurring to pull that tool out before it breaks. So one of the things I want to go through is some case studies that compares the charting methodologies on the shop floor and show you why, if you use a Shewhart chart for precision machining, it actually tells you the opposite of what the condition of machining actually is. 3 groups were sent out to the shop floor to collect data from CNC machining processes. We're going to take a look at the results of 2 of them for time's sake. Each group had 1 person charting X-bar and R, another person charting individuals' moving range, and a third charting with the X-high-low R. A 4th person was charged with observing any changes, tool change, offsets, anything. At the end of the study, the charts and their signals were compared. So here's group 1. It's a CNCOD, and here's the information that they received. If you take a look at the X-bar and R chart and the calculated control limits from that, it looks like this process is totally out of control. You have an extended trend. You have a lot of points that are totally out of the control limits based on the control limit calculations. Is it really that bad? Let's take a look at the individuals chart. It doesn't look quite as bad based on its control limit calculations, but still you have a trend, and still you have points that are out of control. So based on the X-bar and R chart, both of these and the individuals chart, both charts are saying this process is out of control. You need to do something about it. However, if you take a look at the X-high-low R charting methodology, you'll see that it is in very good control. That your roundness is very tight, and all you're getting is a little bit of tool wear to the point where you have to make an adjustment. You make the adjustment, continue on. This is actually an excellently controlled process, and the control charting methodology, when used correctly, tells the operator that you're doing perfectly fine, and it also tells them when to make an adjustment. So what we see is when you use the X-high-low R chart, it's telling you the process is perfectly fine, whereas the Shewhart charts tell you it's wildly out of control. And that's because they are the wrong chart for the job. Let's look at a second one. Here it looks like the process is in control. You have random variation about the mean, and even the individual charts, except for one point, seems to think that this is a very well-controlled process. If you had this on the shop floor, you would say, hey, we're doing really well. But when you take a look at the X-high-low R chart, you'll find out that this process is chaos. First of all, look at the roundness. It's eating up about 50% of your tolerance. That is a very risky enterprise in and of itself. And the reason why the X bar and R chart thinks it's not a problem is because it's picking data up anywhere in here for its data points. It's useless. But also take a look at here. Here's your 75% of the tolerance control limits, and you have portions of the part that are actually out of spec. That again is not a good thing. So this is a very risky, dangerous process, and depending on where you were to measure that part, you would find not only is it out of control, it's actually out of spec. So in conclusion, precision diameters and lengths should be primarily affected by tool wear. Tool wear and associated adjustments for tool wear generates the sawtooth curve. The sawtooth curve's distribution is the continuous uniform or rectangular distribution. The uniform distribution is non-normal and does not follow the rules of normality, such as CPK calculations or Western electric rules for control chart evaluation. The X-bar chart from the X-bar and R charts represent the average of statistically insignificant sample of measurements for a circular feature or even for a length. The R charts represent measurement error, has nothing to do with the process. The control limits are calculated using statistics for the wrong distribution, the normal distribution. The X-high-low R charts represent G/D&T characteristics of a circular feature or of a length. Can you imagine this? You have a charting methodology that actually represents the G/D&T of what you're trying to control. It represents the diameter in the zone represented by the roundness, or in a length, the length and the parallelism for linear dimension. Not only that, it provides more valuable data, such as tool wear rate. In fact, you can determine tool wear rate down to the nanometer. The X-high-low R charts use the correct uniform distribution for precision machining for its calculations. Not only that, you can extend the use to control taper with the X-high-low R charting methodologies. That takes a little more time to explain. We'll have to do that at another point. But it's another very powerful extension of the X-high-low R charting methodologies. Now here's another important point that you need to understand. Automated tool wear compensation is not statistical process control. The algorithm for compensation actually becomes the process, not tool wear. In fact, you can no longer see the tool wear because what it's really doing is an automated over control. It's constantly adjusting based on what it's seeing. So you lose some of the benefits of SPC because the constant adjustments masks that information. It would be handy if the compensation was tracked and added so that you could see what that tool wear rate was. But generally, it's not. So in conclusion, we'll throw Dr. Walter Shewhart out there one more time. The total information is given by the observed distribution. And in this case, the observed distribution is the continuous uniform distribution, not normal. It needs to be handled in its own way. Okay. We made it.
Okay. Thank you very much. If anyone has any more questions, I see we do have a couple of questions here now. But if you do have more questions, please use the questions tab on the GoToMeeting control panel there. Excellent presentation, though. Thank you so much, Mr. Doring.
Thank you.
A couple of people were having issues seeing the slides. I'm not sure if that was a computer issue, individual, or if that was for everyone, because I do see a couple questions here referring to particular slides. So,
well, we are going to provide the slides for you so that on a PDF, so you'll be able to bring them on your own. So that'll help.
Yes, I will send an email to all attendees. That email will contain an attachment, PDF of the slides provided by Mr. Doring. Did you want to take a couple of questions now since we have some time here?
Sure, yeah, let's give it a shot.
Okay, several people are saying, by the way, great topic, excellent speaker, thank you.
Thank you.
So, all right, now some questions are coming in also. So I'm just going to read this first one here. On the control chart for ignoring roundness error slide, I don't know if you want to go to that slide or.
Let me see what I can do here.
Well, the question is, are the lower control limits and the upper control limits actually computed limits, or are they simply allowable limits based on customer input?
I guess I need to know, is that for the X-bar R or for the X-hilo R? For the X-bar R, those are calculated, but for the X-hilo R, those are generally determined by your experience. The starting point is generally 75%. If you have a very stable process, such as grinding, you may be able to extend them out a little bit further. But again, what you're trying to accommodate goes back to the total variance equation. You're trying to accommodate all these other variations and make sure that you have room in case they occur, so that when they do occur, you don't suddenly jump out of specification. So that's why you do a guard banding essentially type of a process for developing your toolware. And here's the thing. Everybody wants to have, an easy way to do things. I want plug and chug and calculate it. But unfortunately, when you're doing it right, you actually have to think, and you have to actually work through this based on experience and understanding of what your process is. That's the only way that it works. There's no plug and chug magic wand that really makes it work correctly. So that goes back to your capability studies and the history of your process.
Okay, thank you. Somebody is asking, how can this be applied in the context of low volume production sizes?
Low volume production. Actually, it's probably the best thing that you can use. Somebody once asked me, how do you do short-term SPC? And I'll tell you what, in machining, there's no such thing. And I'll tell you why. What are you trying to do with SPC? You're trying to find a special cause, right? The problem is warm-up and startup is a special cause. So if you are doing such a short run that your process doesn't even extend beyond warm-up, you don't need SPC to actually determine whether or not you have a special cause. You have one. You're in it. What's nice about the X-hilo R charting methodology, though, is it allows you to react to it in a much more accurate phase. In fact, one of the things about warm-up and startup is you should never start, if you're doing an OD, you should never start at the lower control limit, because it is so out of control. It is so incapable at warm-up that it could actually go the wrong direction as all the different facets of the machine are starting to come up to a continuous process. So I've seen processes that you expect to have the sawtooth curve go up and adjust, go the wrong direction because of all the different effects on the tool pressure as everything's trying to get to steady state. That's just the way it is. So really, do you need SPC to determine that you have a special cause when you know you're actually within a special cause? Not really.
Okay, great, thank you. I think we'll take a couple more questions here. Do you have any suggestions for how to properly chart a distribution where there is a lower detection limit and the process hovers near this detection limit?
So it sounds like we're trying to chart something like a form. So something like a roundness or something where you have a, or even sometimes you have a characteristic where there's a physical limitation where you can't go any further because of certain settings or limitations. That's probably outside the scope of this. That would take probably another presentation. I've been posed that question on several occasions, but this probably isn't the technique that you would want to use for that. Generally, when you have something like you're trying to control a form function, you know that your distribution is going to be a beta distribution or Weibull distribution or something in that family. And you need to deal with it also as a non-normal distribution. So it's a different distribution than the uniform distribution. It needs to be handled differently.
Okay, that sounds
But
like
that's a
an
longer
area
story. I don't think we have time for that.
Sounds like some an area for maybe some future study. Let's see.
Yes.
Someone's asking, do you recommend this chart type for non-features of size, such as surface finish or position?
Not necessarily. Again,
Maybe
this is
another
for
area for
tool
study.
wear. This is for tool wear. So it's designed specifically for the uniform distribution you get with the sawtooth curve. And when you talk about position, again, you're talking about a different distribution, which is more of your Weibull, beta, something that is, what's interesting, let me tell you something that's interesting about those distributions. If you have a form factor, let's say you're looking specifically at surface finish. The better your surface finish, the closer it is to zero, right? The further away it is, the more it's going to be normal. So if you stink, you know, it's going to be way out somewhere you can be normal and you can use a regular X bar and R chart. But what happens is as it gets closer and closer to zero, that normal distribution collides and generates the skewed distributions. And that behavior is very similar to the behavior that you'll see on a Weibull or a beta distribution. So they take a different approach than this for those types of situations. But it is good to recognize that neither the uniform distribution nor the normal distribution, the Gaussian curve, is appropriate for either one of those. So you do need to go and do especially your capability studies based on the correct distribution, and then do a distribution fit to find out which one is correct for the variation that you're seeing. And again, controlling it takes a different methodology, and I guess I need to look at that as a separate presentation because we'd have to go through a whole new thing.
Okay, that certainly sounds interesting. I'm not seeing any more immediate questions. I think a lot of your answers that you've given have answered a lot of the other questions. They're kind of duplicates of ones that you answered. So if anyone
I will
does
say
have,
this. I will say this, if anybody has any questions or has questions, if they go to try to implement this, if they want to have their data analyze. If you need any assistance in trying to make this work, feel free to contact me. I'm always available for that because I really want people to be successful. I want them to get out of the pain of using the incorrect distributions and techniques and get into using the correct ones that are a lot easier and give you a lot more information.
Okay, I was thinking maybe we could provide your email at this time for those who are interested. And you can send Bob an email with any questions or comments, concerns, if you need any help in your data analysis and so forth. And his email is Bob, C-O-B, Doering, which is D-O-E-R-I-N-G, and it's at windstream.net. And Bob's typing that out for us so that everyone can see there on his slide. All right, I got one last question that just came in, and then I'm going to give some other information here. Bob, someone is asking here, is it wise to use PPK rather than CPK?
I get, what was that again? Wise to use?
I'm sorry, someone is asking, is it wise to use PPK rather than CPK?
Well, I'll tell you what. When it comes to precision machining, you don't use either.
Yeah.
How about that?
What we're focused on here.
Actually, it goes back to this. Actually, it goes back to the earlier slides that states that these are the CPK and PPK calculations, and it states that you don't use them if you have one-sided or non-normal distributions because they don't work. They're based on, again, assuming normality in a two-sided specification. So you don't use those for capability when you're talking about the uniform distribution. And again, let me slide down to what you do use. And I didn't spend a lot of time on it because I want to make sure that we made it through here. This is how you calculate the capability for the uniform distribution. You take the upper spec limit minus the lower spec limit, divided by whatever percentage of the specification you're using. So if you're using 75% of the specification for your control limits, you divide it by 75 times your upper spec limit minus the lower spec limit. And that's the beauty of the fact that we're using the uniform distribution, because it goes back to the fact that the uniform distribution, I'm trying to find this real quick here. Oh, we had it, is a rectangle. And the only two things you care about it, there's no sigmas or anything else about this. The sigmas are only there if you have a normal distribution because the normal distribution goes on to infinity. So in order to determine where it ends, we've decided that it ends at plus or minus 3 sigma. But when it comes to the continuous uniform distribution, we know exactly where it ends. It ends between the two locations that we adjust between. So that determines what the capability is, because that's where the variation is going to be. It's going to be where we adjust it. That's it. It's simple. Oh, and by the way, for those people that recognize that you have to recalculate your capability over time because you expect it to change, that's not the case here because this is a constant. There's no recalculation here. So as long as you've set up where you're going to adjust between, that determines what your capability is, pure and simple, because that's where your variation is going to reside between your specification, and that's the definition of capability.
Okay, thank you. Okay, the person just commented it was he agrees, and he's saying it was sort of just a generic question for machine processing overall. So he said thank you.
Well, some of the customers say PPK forget CPK, but you know, okay, what? More often than not, you're only doing it to satisfy customers, but there's something to be. Here's the problem with capability. When you calculate capability, you're using one number, 133, a simple number, to describe the variation that you expect to see over the lifetime of a product in a process. Really? What a magic number that is. One number. I don't want to see one number. I want to see a chart, okay? That number doesn't mean really anything to me. I want to see a chart. I want to see what the data did. I want to see how it behaved. That tells me what's going on. This rubber stamping of CPK and PPK is just so QS 9000.
Okay. All right.
But that's
Well,
a whole
thank
other
you.
presentation.
Yes, certainly we could go on about this.
Yeah.
Okay, so that was some very interesting information. So thank you for taking time to answer all the questions. And we will have a recording of the webinar available on the division's YouTube channel within a couple of days. And you can find this recording at youtube.com/ASQ-STAT-division. So please be sure to, maybe you want to watch the webinar again or share it with your friends, coworkers, colleagues. We also have our other archived webinars available on this channel as well. Also, we encourage you to check out the Statistics Division's LinkedIn page, as well as our events calendar, which can be viewed at asq.org/statistics. This events calendar has all the latest news on webinars, conferences, and many other division-related topics. As I said before, Mr. Doring has generously provided a PDF version of his slides for us, so I'll send those to all attendees within the next day or so. That looks like we are at the end of our time here. So thank you, everyone, for joining us again, and Mr. Doring for the presentation with the Statistics Division. And we hope everyone has a wonderful weekend.